AI drug discovery. We have two arms in the company. We started looking at deep learning and specifically generative AI from very early days of the entire field in 2014, 2015, when there were first papers on generative networks, adversarial networks were published. We started experimenting with those architectures, and our first peer-reviewed paper on generative AI for chemistry dates back to 2016. This paper is called Chronocopy of Meaningful Leads. It uses max chemical fingerprints and adversarial autoencoder architecture to generate novel chemotypes, novel molecules, small molecules, predominantly. I think this is the first peer-reviewed paper in the field of generative chemistry. And following that, we have been working on experimenting with different architectures and seeing what works. Because unlike ChatGPT, in our field, we have to actually go in the lab, synthesize a molecule, and test it. So we need to have an experimental validation to figure out if it works or not. So we spent time and resources. So we were fortunate to kind of enter the field first, to have this luxury of time. And we published a bunch of papers with validation, experimental validation data. And currently, yeah, we have published over 20 papers in generative AI for chemistry field. And we've also established a benchmarking platform called Molecular Sets for small molecules. So many players and labs who work in small molecule space for drug discovery use this benchmarking platform to assess performance of the new architectures. So following that, in parallel to that, we have been building an operating system for generative AI for chemistry. We call it Chemistry 42. It took us a long time to build. It has, in a nutshell, it has two main components. It has a library, a zoo of generative models, and many reward modules, reward functions, merit functions that assess the quality of generated structures and feed the reward back into the generative model. So if in the simplistic terms, it works in the following way. Once a user defines an objective, our target product profile, what properties does the user want to see in the molecule, the generation starts. Currently, Chemistry 42 has over 40 generative models, predominantly focused on small molecules. And the model, the platform goes through millions of generatives, iterations, and generates ideas on different chemotypes. And every single molecule is processed through the reward pipeline that has a 2D and 3D assessment components. And in totality, it is comprised of hundreds of different functions, scoring functions, predictive models. And ultimately, this system, reinforcement learning system, helps the platform navigate the chemical space into the right direction, into the right kind of chemical universe. So the chemical galaxy. So basically, we've established this platform, and since then, we've been exploring ways how the platform can be used in drug discovery. And it turned out that it can be used across many target families. It's a busy slide, but it represents what we do right now as a company. So we have an AI platform, and the Chemistry 42 platform is a flagship platform for chemistry that allows us to create drug discovery programs, like actual small molecules that go into clinic and go after specific diseases like lung fibrosis. Last week, we announced exciting phase 2A data with efficacy of our molecule generated by a generative AI platform. In lung fibrosis, we have many oncology programs in clinic. and many are coming into human clinical trials soon. So we already see the tangible effect, but tangible results from the platform on drug discovery field. And about 4 or 5 years ago, we started exploring other directions where the platform can be utilized. And one of the directions which we went to, and we were inspired by actually talking to Aramco, is like gas capture and materials and petrochemistry. So we had wonderful projects in petrochemistry and octane number prediction, modeling, and one of the kind of inspirations was also topic of gas capture, both carbon dioxide and hydrogen storage applications. We've also expanded into draft academic paper writing software. So if you are drafting academic papers, you can test it out for free. It's called Dora. You can find it on our website. It's a tool that automates paper writing and helps manage references, etc. But ultimately, what we kind of where we are moving as an entity, we kind of showed that the platform is applicable to drug discovery. So we see multiple examples and publish multiple peer-reviewed studies on successful applications of generative AI platform for drug discovery. Now we went into sustainability, and in sustainability, we have successful use cases in agrochemistry. We have partnered with a great company focused on agrochemistry called Syngenta. They're a UK and Switzerland-based company that generates sustainable manufacture sustainable herbicides and pesticides. So we partner with them on using generative AI for those applications. And beyond that, we went into the field of gas capture, base oils and lubricants, and we are actively exploring applications of generative AI in those areas. What we saw when we entered that field, that very few benchmarking platforms specifically for generative AI were available. So we decided to make our own, like a initial kind of step towards that direction. We decided to make an open source platform for, we call it environmental sustainability. It's a broad, like it's broad term, and because we cover different fields of focus where we had experience, applying generative AI in gas capture, in carbon capture, hydrogen storage, hydrogen capture, agrochemistry, so generating novel herbicides, pesticides that are greener, safer. You can synthesize them more easily, so the cost of goods is less, the pollution is less. So it's a big like volume of production in agrochemistry field. So it's also pretty relevant for the area of sustainability. Base oils and lubricants as well. It's a huge industry and extremely high volumes of production. So what we wanted to achieve in setting up this consortium is to first and foremost create an AI model benchmarking medium, like platform, where people can benchmark their models across many different domains, enable data sharing and knowledge exchange. And we kind of started working on this. The first application is agrochemistry. And as I mentioned, we have been working with Syngenta in this specific field for quite a while. In its essence, it's very reminiscent of drug discovery. You have to optimize for many different properties simultaneously. Your product has to be potent against the target mechanism. It has to be synthetically accessible. It has to have like selectivity between crops and weeds. it has to have like a physical chemical profile that would have the right properties for application in the right season. So there are many different properties that require multi-parametric optimization. So what we did is that we adjusted and customized our Chemistry 42 platform, added custom generative models, what are more applicable to agrochemistry, added external rewards via API, predictor specific to agrochemistry, chemical filters, we call them MCFs, were added that are agrochemistry specific. And by adding those kind of custom parameters, we're able to guide this process into the right, the generation process into the right chemical space and generate tangible and tractable agrochemistry products. So that's what we have achieved. And in the consortium context, we have set up this folder in our GitHub repo, and we are currently working on integrating state-of-the-art model for agrochemistry and creating a workflow where we would assess novelty, diversity, and quality of generated structures in an automatic way. So that's kind of a work in progress. We will upload the first workflows hopefully within next 2 weeks. And please feel free to reach out and contribute. But the vast bulk of kind of work to date, because we released the consortium just over 2 months ago, is around gas capture, and this constitutes primarily carbon capture and hydrogen storage applications. So we have set up this repository on GitHub. You can visit it and contribute. We are currently all open to any collaborations, any ideas, any feedback, especially negative feedback. So we would like to improve the platform. Currently, it has the GitHub repository has 3 folders. One is related to agrochemistry, one is related to gas capture, and the third one is related to lubricants, base oils and lubricants. And there we want to enable also both generative and predictive modeling of compositions of lubricants and base oils. In terms of gas capture and carbon capture, we incorporated 2 main assessment workflows. One is based on Grand Canonical Monte Carlo simulation, which we adopted from MOVDIV framework. And another one was adopted from MOV Transformer framework, where we fine-tuned MOV Transformer on specific predictive tasks on specific properties. So in its essence, right now the benchmarking for gas capture is able to take in a data set of CIF files and benchmark them against many properties in automated way. And you will get kind of a leaderboard ranking of all the molecules, all the CIF files from your list, from your data set. So we currently have 4 models in profiled in the benchmark, and we are welcoming everyone to contribute more. So I've kind of a framing backstory on how do we digitally store MOVs. So there are a few ways. The most common ones is use the CIF file, crystallographic information file, that contains information about topology and atomic positions and of the material. And MOVs is the most abundant, metal organic frameworks is the most abundant data material type in terms of data availability. That's why it makes sense to start with it. We're very much open to other material classes. We want to make this benchmarking platform applicable to all types of materials. So yeah, CIF is the most commonly used one. The file itself contains all the information about topology, coordinates, and the formula information, as well as user comments could be provided. In terms of alternatives, one very prominent format is another one prominent format is MOFID, introduced by Snar and Landsberg-Gudzik's labs, and this format actually simplifies MOF structure into a sequence of blocks. It's almost like a smile string in a small molecule space where you have inorganic and organic blocks. You have topology information, and the entire sequence of the molecule, topology of the molecule, can be encoded into a string format which can then be fed into many different models, like architectures that work with string formats. So it's very convenient way to represent a molecule. And yeah, the way it works, it's kind of it breaks down the MOF structure into metal nodes, organic linkers, and incorporates topology information and creates a sequence, a string that can later on be encoded and used for the training and generation purposes. Now, what data sets we started with? Because we had to start with specific databases to fine-tune our models on, and we chose 3. By no means an exhaustive list. This field of material, specifically metal-organic frameworks, are very rich. In databases, we chose BWDB, which has 320,000 CIF files and measures 36 properties. MOFAX-DB has 150,000 CIF files and 143 properties, and ArcMof is 279,000, 27 properties. We use those data sets to fine-tune MOF transformer embeddings of MOFs into predictive models, and use those data sets to actually, to make those predictive models. In terms of dataset structures, it is very well described in the papers, but BWDB in short captures basic CO2 properties like uptake, heat absorption. We have nitrogen uptake. We have geometric properties. Selectivity is important, very important property, and some other properties as well. So it's a very good and exhaustive database to utilize. MOFAX-DB has additional properties like hydrogen uptake. MOFs can be used to capture hydrogen. It's one of the common applications as well, beyond CO2 capture. So we used MOFAX-DB hydrogen uptake data to fine-tune the MOF transformer model to capture that. The database also has nitrogen uptakes and methane uptakes as well at different temperatures and pressures. And in terms of ArcMof, we have, again, CO2 uptake, hydrogen uptake, and nitrogen and methane. In terms of common properties, across 3 databases, we only have 2 common properties. It's CO2 uptake and nitrogen uptake, but across the board, we have some common ones between the 2 databases, like selectivity, and hydrogen uptake is also shared by MOFAX and ArcMof databases. In terms of adsorption model, so we actually use Langmuir adsorption model to predict extract properties under low pressures, 400 ppm, and enrich this database to later on fine-tune MOF transformer to be able to predict CO2 uptake and different hydrogen uptake at those pressures. This is basically how it was calculated. It's a very well-established model, and we calculated missing data points at low pressure and basically enriched the entire database with those measurements. So what models did we use to set up the benchmarking? We used 4 models. The first one is MovDiff. It's a popular model based on the diffusion algorithm. It has a tremendous kind of backend with many different pipelines embedded in it, and MovDiff operates on it uses MovID for kind of uniqueness and material matching, but it also can generate materials beyond MovID. MovFusion is again a diffusion model and generates materials from scratch. And MovReinforce also uses a reinforcement concept where we can basically have an active learning loop with predicted properties like carbon dioxide uptake in the generation process. So all those models are well established. Some of them are more new, like MovReinforce has been published this year. And you can read up on them using this links information. And one model that we've introduced, it's called Nudge Zero, and I'm going to spend a bit more time on describing it. So it's a recent model that we've co-developed together with NVIDIA. It's a multi-model transformer model that can work with text, chemistry. We published it in a chemical science journal. In essence, it took into during the training process, and for this model we used a T5 architecture described in a previous presentation, previous session. We used this architecture and vast collection of text data and chemistry data to train the model. And the model is chattable, so you can see the right the chat chat box, where you can ask it questions about specific targets, mechanisms. You can also ask questions about the chemistry. It can interpret smile strings and generate smile strings, visualize them, so it can generate images, and predict properties, right? So you would want to ask it what solubility is a smile string have, and it will predict the solubility. So it's a multimodal architecture. Again, we published it early this year, and it's available on Hugging Face, so it's publicly available. You can check it out and test it on your applications. So we use this architecture and fine-tuned it on 2 databases out of 3, DWDB and MovXDB, primarily because we also wanted to have additional properties in the data set. So we fine-tuned Nudge Zero on those databases, and we're able to train a model that will generate CIF files, atomic coordinates and topology data based on the input prompt. So we can give it a prompt, like you want to generate a MOV with a certain CO2 uptake at certain pressure and temperature, and it will generate materials, or like collection of materials. The number you can specify the number you want to get. Now, this model, the fine-tuned model, will also be made available. We're working on kind of finalizing and releasing it, but the results are already included in the benchmark. Now, how do we benchmark? And as I mentioned in the beginning, for gas capture, we have 2 main workflows for benchmarking. One is a grand canonical Monte Carlo like simulation adopted from MovDiff, so it's a standard workflow. And another one is a MOV transformer approach where we fine-tune MOV transformer-based embeddings of MOVs on specific tasks. Now, for Grand Canonical Monte Carlo, we combine RASP2 tool with eGulp to build a workflow, and the following properties are predicted for using MOVDIF simulation. So we predict working capacity, selectivity, CO2 uptakes, different pressures and temperatures, heat absorption, nitrogen uptake, and heat absorption for nitrogen. As understandably, Grand Canonical Monte Carlo simulation is one of the most frequently used and adopted ways to approach this, but it is slow and it is kind of like computationally intensive. So part of the reason why we adopted MOV transformer is just to make it faster, make this prediction faster so we can iterate quickly. So yeah, MOV transformer, you can read up on it, and it was published in Nature Machine Intelligence last year, pre-trained on 2 million structures using topology, void fraction, and building block tasks, and can accurately generate embeddings for materials, for MOVs, and use for different tasks. So what we did is we fine-tuned MOV transformer on the following properties extracted from the free databases I mentioned before, I described before, and focused on the following properties. So the following predictors have been included in the workflow, so you can use them from our GitHub repository. CO2 uptake at different temperatures and pressures. So those predictive models have been developed and they're stored there. Heat absorption, working capacity, landfill working capacity, and also selectivity against nitrogen, methane uptake, and hydrogen uptake was also used to fine-tune the models. And the entire MOV transformer was sort of fine-tuned, right? So we had this predictive layer at the end of it, predictive head of the MOV transformer, but during the process of fine-tuning, we have kind of retrained the entire model. So those models have been established, and you can test them. What we also added is properties for nitrogen uptake and some electronic properties. So yeah, again, whatever was available on in the free databases we selected, we fine-tuned on that. In terms of performance and how it correlates with Grand Canonical Monte Carlo simulation, I think we achieved reasonable performance in terms of R² and mean absolute error for many properties. So you can see here some of the kind of snapshots for like most frequently used properties, and the performance time is significantly faster, right? So you can use MOV transformer for speed, and it will be sufficiently accurate for many tasks, for many core properties, target properties, what you would want to achieve. So right now, the repository contains an automated workflow that has both MOV transformer and Grand Canonical Monte Carlo simulation workflows that will take in your sample zip files and run them through the process. And for every property, we will have data for coming from MOV transformer and simulation, Monte Carlo simulation workflows. So that is automated. And ultimately, we will end up, and currently we're working on different ways how we can build different leaderboards of models. We only have 4 models right now, but the most kind of logical leaderboard is just to have top materials by different properties. This is an example of materials that were generated by different models, 4 models. And the leaderboard and the table was sorted by predicted CO2 uptake. So you can see, a prefix means the model name. You have MOVDIF, you have NATG0, MOV reinforce is here as well, and MOV fusion is here, right? So you can add your own models and add your run them through run those CIF files generated by those models through this workflow and add your results to the leaderboard. So that's a very convenient way to do that. And ultimately, you can summarize the performance of the model by the performance of top material. And currently, we're also working on additional metrics, aggregate metrics for model performance, how we can assess the quality of generation in totality, like the number of structures, novelty, diversity, those sorts of properties. We're also working on integrating them. So it's still early days for the workflow. And in terms of contributing to the table, it's very straightforward. We have installation instructions. You need like a Docker, Python, and a server or computer with a GPU. And you can provide it a folder with your CIF files around the workflow and just submit a pull request in the end to append your results into the summary table that we have in the repository to add your files. Now we invite everyone, all scientists, individual researchers, academic labs, institutions, to share ideas, contribute. So we are very much open to any collaboration, knowledge exchange. We have more information about the consortium also on our webpage, just nsilico.com/sustainability. You can email sustainability@nsilico if you would like to learn more or join the consortium, or this is my email. You can send me a note as well. The consortium is for everyone. So any individual scientists who would like to contribute, discuss any ideas. So no requirement to join the consortium. Just send us a note, and we'll be happy to feature you on consortium page, and we'll also promote the consortium on our kind of social networks. Importantly, this consortium is done in collaboration with University of Toronto, so Alana Spurt-Gudzik Lab and Acceleration Consortium. So they're an amazing group of scientists that has expertise in many different domains and many different areas and have substantial experience working in materials. So we have regular meetings that consortium members can participate in and attend, and join the scientific discussion to establish kind of future directions for the consortium and the roadmap. Yeah, let me stop here, and happy to take questions. Maybe I can take them kind of offline in the chat box. Thank you.
Thank you very much once again, Dr. Alex Aliper. This is very inspiring presentation, and it's a nice invitation to all people to basically join this consortium. And the work is truly transformative, and just like sets the high bar in the field, as we can see. So I see 2 questions in the chat. First one, maybe we can take some. Can these data sets be accessed and analyzed in ChatGPT? So that was one question.
Well, nowadays you can do anything in ChatGPT.